to just regular derivatives without the formula, what is the pattern that they take on? So if I was to give you this one, for instance, that's not up. Oh, give me a second.
Oh, is the base time lines?
There we go. Yeah, so y equals 5x squared. What would be the derivative of that function?
Oh, there you go.
Instead of y, what do I do to make it y dash? Y dash. Or you could also say, it's doing this to me again. There we go. You could also say dy dx equals is another way of saying y dash. I generally stick with y dash because it's easier. You could also, if I had have said f of x equals, you'd say f dash of x equals. So this one, that would become 2 times 5x. And what do we do to the power? Minus 1 off it, so that would become 1. What would this one become?
Why don't you times that and make it 10x1?
Oh, I just didn't go to the next step. That's why. Let's give you a sneaky one.
Where's the X? Oh. Can you give us
Yeah, I'll give you a moment. Have a crack at that one, guys.
So if it's got no power of x, you just remove it, and actually 10 1, it's 11 10. And 3.
If it has no x at all, gets dropped off. They're really easy when we're differentiating, which is what we're doing here. When we get to integration, which is when we then go backwards, those dropped numbers actually become a real pain in the butt.
Finding derivatives with respect to x is what we see.
And we're only finding derivatives of polynomials, guys, at the moment. There are rules for you can find the derivative of like sine x. We're not going to look at that just yet. What? Chapter 13. What's a half of 10? A half, 1. So what's half of 10? 1. Half of it. It's half of 2.
Okay.
Or in other words, you're dividing by 2.
Yeah.
Wow, I literally almost 50% overlap between this class and physics now. Over 50 if Ryland moves in. 100% if the rest of you move in, just saying. Just come to physics. There you go. Sorry? Is that at the same time as physics?
Into physics, it's on our way.
Okay, the first one, guys, 5x cubed over 6. What would we do to that one?
You're gonna fit it in.
Yes. I would simplify the top and bottom because they both have a factor of 3 in them. So I would make that 5x squared over 2. But that would be equally as correct. But you want to be in the habit of cleaning it up where you can. So I'm just gonna, as we go, I'm gonna do any cleaning up I need to. So that would be 5x squared over 2. Okay. 2x to the power of a half. What would that be? It would be a half times 2x negative a half. That's right. So when you take 1 away from a half, you go down into the negatives a half. And then let's clean that up. What's a half times 2? 1. And we don't like negative powers, do we? So we're going to put that on the bottom of a fraction to make it a whole number. 1 over x to a half. What happens to the next number, minus 10? Just minus 10. And we drop the 3 because it doesn't have an x attached. And this is very much the only x's club. We're differentiating. Why would we only care about the terms that have an x in it? Think about what a derivative shows you. Sorry? I've heard like this is because the plus 3, think about our sine cos tan stuff. If you change the d value of a sine cos tan, all that does is move the function up and down. Does it affect the slope at all? It's the same in a polynomial. All plussing a number without an x does is it moves the function up and down. It doesn't change the slope. So because all we care about is the slope, any number x affects the slope. Anything without an x does not. Cool. That was just a bit of recap from Friday's lesson. Was anyone away Friday, by the way? I don't think so. Yeah, cool. And we skipped that little bit, and we got here. Okay. Well, good news, people in physics, because we're doing some physics today. Displacement, velocity, and acceleration. So, for those of you not in physics, displacement is another word for distance. I wouldn't. I wouldn't. Velocity, what's that another word for? Speed.
Acceleration speed.
Acceleration is acceleration. It's different than speed.
Yeah.
The main difference, we don't really need to worry about this in terms of mass. The main difference between distance and displacement, if I walk to my house let's say it's 2 k's away, that means my displacement is 2, my distance is 2. I've walked 2 k's and my displacement is 2 k's. If I, however, then walked back here, how much distance have I traveled? 4, but my displacement would be 0, because displacement is your distance from where you started from. So if you go in a circle, your displacement is 0, but your distance will be bigger. So that's the only difference between distance and displacement. Velocity and speed, exact same thing. Speed is just how fast you're going based on your distance. Velocity is how far you're going based on your displacement. So in that same example, if I took an hour to walk to my house and back, I've gone 4 kilometers an hour as my speed, but my velocity would be 0 because I have not moved from my starting point. Well, I've ended up back at my starting point. I did move from it, but because the distance from my starting point is 0, my velocity is 0. Okay, that's all there is to it. Now, just going to do this on the side. Displacement is your distance from starting point. Your velocity is how quickly your displacement is changing. So think about that in terms of speed, guys. If I am running really, really, really quickly, I have a high speed, which all that means is that I'm covering distance very quickly. If I had a lower speed, my rate of change of my distance is lower. So velocity and speed are both measures of rates of change, how quickly our distance is changing. Okay, I'll say that again. Velocity is a measure of the rate of change of displacement. If velocity is a rate of change, if I gave you a function for displacement, how could we find the velocity?
Over time.
We could do like a graph or something, figure it out over time. With what we've learned, what's a derivative? It just shows you the rate of change of something. So if I have my displacement and I differentiate it, that will give me my velocity, because the velocity is just the rate of change of my displacement. Then my acceleration is the rate of change of my velocity. So guys, this is something that always throws people. I'm just going to put in our units as well. When we're talking about displacement, it would be really convenient if the regular letter to use was D for displacement. For whatever reason, that's not the letter. They use S. Just S. And it's measured in meters. Velocity, we do use V for, and it's measured in meters per second. So that's the physics way of writing it. You could also write it meters per second or meters per second like that. I don't care what you do. The first one is the physics way of doing it. The other two are just the more general ways of doing it. It's up to you what you use, whatever you're most comfortable with. Can you see that the -1 above the S is just because the S is on the bottom of the fraction? I've moved it to the top of the fraction. That's it. That's all it means. Your acceleration, A, is meters per second per second. Now that throws people. Think about it this way. The acceleration due to gravity, you might know, is 9.8 meters per second per second. What that means, if I jump out of a plane, after 1 second of gravity working on me, I'm traveling 9.8 meters a second. After 2 seconds, it increases by 9.8 again, so I'd be at 19.6 meters per second. After 3 seconds, I'd be going another 9.8 meters a second faster. So that's what the meters per second. This is how much our velocity changes per second. Each second we get 9.8 meters per second faster. So the other ways of this would be m over s squared or m s squared. Up to you how you do it. Okay. Let's have a look at these problems in a second. I went to drink, and that is not my water bottle. Remember during COVID, someone was like, I think someone actually did drink the hand sanitizer, which was sorry? Well, I'm sorry. Who told what? He said drink bleach, I'm pretty sure. I'll be honest, I don't know that, like, it was so much of a joke or that he's just very dumb and didn't think about what he was saying. Okay. I wonder, like, how good YouTube's, like, algorithms are. Can it just talk that we were talking about, like, hand sanitizer and drinking bleach? Will it, like, have, like, will it be, like, under the video, will we say, like, COVID-19, more information can be found? Like, you know how when there's, like, misinformation videos, they have that little thing on it? Okay, let's have a look at these ones, guys. So we're going to talk about graphs of displacement, velocity, and acceleration. So we're going to be looking at things like what is it increasing at a steady rate? Is it increasing at an increasing rate, increasing at a decreasing rate, all that jazz. And yeah, we'll be looking for the link between the three. Rate of change of velocity. So we use the letter A, and we use the descriptor ms -2, meters per second per second. For the non-physics people, is that making sense, the meters per second stuff? It's how quickly your velocity is changing, so how much your velocity goes up by per second. Or 1, 2, 3, 4. Alyssa pretty much counts because she's been in there for 70 minutes. 5, 6, 7. 7 people haven't done physics in here. Physics is easy apart from the assignments, I think, which are a pain in the butt. But anyway. Okay. Let's roll, guys. So for each graph, comment on how the distance changes relative to speed, what is a possible fit for the data, and what is the average rate of change. So this one, we don't have axes. You see we're starting at nothing. And then after 5 seconds, we've gone... Oh, so these are all, distance relative to speed. So after 5 meters, we're going 10 meters a second. Okay. So is this a constant increase? Yep. So this is a constant rate of change. Can you think of a situation where you start going 0 and then you steadily increase your speed fairly quickly? So after 5 meters, you're going very quick. Yeah, car at a stoplight. They put that. Yeah. So this could be a car stopped and then going to taking off. I don't know. 10 meters a second, that's pretty quick for someone running, isn't it? Like, that's 10 meters a second is Usain Bolt speeds. Oh, what are you doing in school instead of winning millions of dollars and sponsorships and stuff? And our average rate of change there, guys, just be delta y over delta x. So we've got change in y, it's gone up by 10. Change in x, it's gone across by 5. I would say as well, if this was someone running, like a human gets to their top speed pretty quickly. So a human running would start here, and they'd burst up to their top speed, and then they'd sort of flatten out because they're running as fast as they can. And then, do you know how long people can sprint for?
4K to my max.
I'm just going to stop listening to Rylands today. I believe, like sprint is 9 or 10 seconds. But then isn't it like you can only like run about 400 meters before you need to slow down a bit? Because that's why they have, like, if you see the difference between 400-meter runners and 800-meter runners, the 400-meter runners do like a much quicker pace than the 800-meter runners. Like the 800-meter runners take more than twice as long to do that race because like we physically can't run for that long. So yeah, anyway, that's a random aside, which I never do, but just in that one situation, I thought, why not? Okay, this one. We actually have a starting speed. So at time zero or distance zero, whatever, it's actually already accelerating. Is this one got a constant rate of acceleration? How would you describe the acceleration? Exponential. So it's increasing at an, yeah. So this one's increasing at an increasing rate. Can we think of a situation that this might represent? Does that look like it's slowing down anytime soon? Justin, was that a thought? Nope.
Fuel price.
Unfortunately, fuel prices aren't tracked by distance. What's something that just goes like that? Yeah, rocket.
Rather
If I write it down, will you stop saying it? Island running. Brackets. He is on a rocket.
Can you run on block?
again.
Probably not at those accelerations. Yeah, so at that, well, we'll look at what the acceleration is in a minute. But I think fighter pilots can tolerate like 7 or 8 Gs. So when they do like a really high speed maneuver, they might have 7 or 8 times the force of gravity on them. And even then, like their vision goes blurry, it goes tunnel vision, and they're like struggling to stay like not passed out. I think 2 to 3 Gs, most people struggle to stand. So if we're going like 18 meters per second on a rocket, you'd be struggling to stand up, let alone move around. I just had a flashback to my like childhood, and like not on a rocket, but like, did you guys didn't have Cheese TV when you were growing up, did you? Like that's a '90s thing. It was like on the mornings on Channel 10, it was like these two dudes that were like hosted a show, and they do like dumb skits and then would like go into cartoons. And they used to have like, what did they have? They had Dragon Ball Z, they had Pokemon, like those kind of ones. And I remember for a while just like it fit with the time I was going to school, that like I'd watch Dragon Ball Z and then when that was done I'd go to school. And I just remember they had like a section of the show where like the main character was like traveling to another planet, but he wanted to like, he was going there to fight someone. So he turned like the gravity up to like 5 Gs and was like doing workouts in 5 Gs and stuff to make himself tough. And that just like sprang into my head then. While Ryland is running around the rocket, maybe he will have those sort of takeoff speeds after he's been training in 5G. I don't think it's. It was actually shadow puppets. Like they didn't have TV when I was around. Okay, let's calculate the average rate of change. This one's going to be a real pain in the butt. Okay, I can see here it has a coordinate at 310. And I guess we'll have to use this coordinate here, which is like 0.5. Will this line of best fit give us a good approximation of the slope? Yeah, it'd be alright. It's not going to be fantastic. Especially at that 310 point, you can see that the actual slope would be more like that, much more steep. It's going to be a huge number. But anyway, let's figure it out. Change in y over the change in x. Should probably use the Greek letter D. Equals 10 minus 0.5 over 3 minus 0. So 9.5 divided by 3 will be 3 point something. That's not my calculator. My goodness. So 3.16. So our average speed is actually our average acceleration. Sorry? It shouldn't be.
0 to the other one goes 0 to 10. No, it goes 0 to 0.
We don't start at 0. If you look at I meant to put -2 on this one. The reason why is because it told us that this is comparing our distance to speed. So we're finding the rate of change of our speed, which means we are finding our because acceleration is how quickly our speed or our velocity is changing. So these are acceleration calculations that we're doing when we're finding the average rate of change. Yo. Nothing. I'm not consistent. That's the secret for when I'm just being inconsistent. I'm just exposing you guys to different methods of doing it.
What?
Maybe. What about this one, guys? Yeah, this one could be a runner. Or what's our rate of change by the way? Is it constant? Is it increasing? Is it increasing? It's increasing, but the rate it starts really quick and it starts petering out. So increasing at a decreasing rate. This could be a runner in a race. Probably not. But I just want you to be thinking about what the graph is showing you. I'm actually not going to bother finding the average rate of change on this one because there's no nice numbers to use and I'm slack. So we can see though that if we use this one here, and I don't know, that one there, run it in a race. Can you see that that's not a very good approximation? Which is why I'm not really going to worry. You use like that. That would be a good point to use, but no matter what approximation we use, if we're using one segment, it's going to be dodge. Like that would give us a good approximation of this top bit, but the bottom bit is then being completely excluded, and that's where a lot of your acceleration happens. Yeah. Okay. So, what are you finding when you find the rate of change of a displacement function? Velocity. So velocity is the rate of change of the displacement. Therefore, if s equals some function, remember s is displacement. If it equals some function of x, velocity is just the derivative of that function of x. So in other words, v equals the derivative of s, if you want to think of it that way as well. Questions, comments, concerns? No.
What's S again?
Displacement. I've become very keen for lunch all of a sudden. Just thought I'd share that, you know.
What do you have for lunch?
Pork tacos. Tacos.
Oh,
Soft tacos. Ooh, I like that idea. All right. We good to go, guys? I don't know why I gave so much room for this answer. It's going to be about the same size. Right. Right. So, similar relationship happens when you find the rate of change of the velocity function. So, for this one, if velocity is equal to some function of x, acceleration is just going to be the derivative of that velocity function. So, in other words, acceleration is velocity differentiated. If you have a velocity function and you differentiate it, it gives you the acceleration. Because the differentiation just finds the rate of change, and all the acceleration is the rate of change of the velocity. So if you differentiate velocity, you're finding the rate of change, and our word for that is acceleration. I don't know why there's this one random, they've used all this physics language in methods. It's the one time it ever happens, but just for whatever reason it pops up here. It is a pretty natural link between the two things, but there you go. So in general, guys, though, if I have my displacement equaling some function of x, my velocity would be the derivative of that, and my acceleration would be the second derivative of that. You just differentiate it again. So if I give you something's displacement to get the acceleration, you just differentiate it twice. Pretty easy. Pretty chill. Another way you could say it, say your acceleration equals your velocity differentiated, which equals your displacement differentiated twice. I wouldn't say it that way. I think the left-hand side is probably a bit clearer myself, but that's up to you. What makes sense to you? Do I have any questions, comments, concerns on those ones? You have a conniption about it? I'm surprised about that. Can you look to me as someone who has quibbles? Okay. So, guys, the displacement of a particle is given by y equals x cubed minus 4x squared plus 3x plus 5. So that tells you how far away from the origin it is at any point, how far the vertical origin is, and x is our time in seconds. So obviously this function's doing some crazy stuff, flipping all over the spot. Yes. Okay. We ready to do this one, guys? Ryland, we ready to do this one? Let's roll. So I have the rule for displacement. Now I'm going to do something a little bit different here. It says y equals 2. I'm going to say my displacement as a function of x equals x cubed minus 4x squared minus 3x plus 5. Now, I want to find the velocity function. How can I find the Oh, whoops, plus 3x. I want to find the velocity function first. So my velocity is just going to be equal to the derivative of my displacement function. What is the derivative of 3x cubed, rather? 3x squared. What's the derivative? Minus 8x. And then the 3 becomes plus 3. And the poor little 5, we don't care about.
Well, that was easy, wasn't it?
Uh-huh. Question? That looks like a concern right there. What are you drawing on your face? Okay. So we all good, Sky? So remember, if this is my function f of x equals, I don't know, nx to the m, if we're just using letters, the derivative function, so the rate of change of that original function, I take the power and I multiply it out the front, and I subtract 1 from the power. So for x cubed, I took the 3 out the front, multiplied it through, then I reduced it down to a 2. So we got 3x squared. That's why the 5 disappeared, yeah. Okay, so for the acceleration now, guys, my acceleration is just my velocity differentiated. Do what again? Yeah, we differentiate again, which is just the second derivative of the displacement. So all we do is I take 3x squared, I differentiate it again. What's that give me? 6x and minus 8x and plus 3. Nothing.
How do you get 6x, right?
Well, 3x squared. Drop the 2 down in front. 2 times 3 is 6. Yep. Okay. That's all for A. Because in my first line, it was a plus 3x. So the x has a power of 1. So you drop the 1 down in front. 1 times 3 is 3. And then 1 goes to 0, so the x disappears. Okay. Calculate the displacement, velocity, and acceleration at x equals 0, 1, 2, and 4. This is going to be a pain, so I'm going to draw a table, I think. So I might just rewrite it out nicely. S equals x. Why am I using this color? Let's go back to red. I'm enjoying writing in blue lately too. Because it's not one of the preset colors that I can just tap. I'd have to go into it and muck around to get it. So that's my displacement function. My velocity function now is 3x squared minus 8x plus 3. And my acceleration function is 6x minus 8. Okay. Now, for each of those 3 equations, I've been asked to find a value for when x equals 0, 1, 2, 4. Who wants to do those 12 workings outs? Not me. I certainly don't want to. Is there a shortcut way where I can do all of that math without really having to do any effort at all? Can I get you to grab out your graphics calculators, guys? Okay. Can you click y equals 2?
Increase validation. Why?
Okay, y equals 2. Sorry, my emulator, Mr. Todd's working on getting us access, so I can still use it. For the first one, just put in your displacement rule. X cubed, top left. X cubed minus 4x squared plus 3x.
What?
It's a rubbish.
So once you've got your three equations in, can you put your calculator down on the desk just so I can tell that you're done? Displacement, velocity. So y1 equals, put your displacement. I think I said y equals 2. Okay. Nope. You just need to realize which one is you need to realize which one's acceleration, which one's displacement, which one's velocity. It's the only thing. So if you put displacement first, velocity second, acceleration third, you should be right. So once you got them in, just calculators on the desk. It's very good. It's very cold.
I hate it when it's dark.
I was watching David Attenborough last night, and it was like all about like melting ice and stuff, and just seeing these like starving polar bears. It made me sad. My water bottle is more icy than their hunting grounds at the moment.
It's horrible.
Well, it's interesting. Like, I won't get into it. Well, that really gets into the question: is do humans have equal rights? Like, do humans have rights?
I would say
Like, can you look out there and see a right hanging in the air? Like, rights don't exist, is what I'm saying. So the reason we have rights is because as a society, we've agreed that like there's a way that we should be acting. And then if you don't act that way, you can be punished. So you don't like that. Okay.
Very good.
Well, like what I'm saying is, do I think animals have equal rights? Yeah, what I'm saying is rights don't exist. So either society thinks that they should or society thinks that they don't. Doesn't really. But what if their owner like wants to breed pit bulls to fight each other? Should that be accepted by society? Yeah. Because people bet on the fight, so they put the two, like boxing, they put the two dogs in and the winner, like, they put bets on. Anyway, looks like everyone has that in their calculator. Can I get you, in your calculator, if you look next to the y equals button, there's a button that says window. Don't press it.
Press it.
But if you look above the window, it says table set. We want to set our table up right. So can you go second window to get the table set menu? Table start, you want it to start at 0 because our first number is 0. And then we go up in ones. We do skip 3, but we're going up in ones. So if it's got that, if you look across to the very right-hand side, it says graph. Don't press it because we actually want the table, which is second in graph. And you should see a big spreadsheet of numbers there. That has subbed in X at 0, 1, 2, 3, 4, 5, blah, 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 blah. Not that I know of.
I should make that.
Okay, so for our values, guys, we have our displacement our velocity and our acceleration at 0, 1, 2, and 4. At 0, what is my displacement? 5. At 1,
5,
at 2,
3,
and at 4. My velocity at 0,
3,
1, 2, and 4. Okay.
four,
and 16.
Okay. So that's a bit of a wild table there. Actually, are we getting faster or slower? How would we tell if we're getting faster or slower, by the way? Which number? Displacement, acceleration, velocity.
yeah,
Same. The same.
How come this one has an x7?
The question.
X cubed minus 4x7 plus 3. Okay, we would look at our acceleration to figure out if we're speeding up or slowing down. So at time 0, is our particle speeding up or slowing down?
speeding up.
It is massively decelerating. Because if you look, we've got negative acceleration. So that means it's actively losing its velocity. Its change in velocity is negative. At time 1, is it speeding up or slowing down? Or sort
It is
of.
speeding up from the first one, but it's still.
It is still decelerating, but it's not decelerating as much anymore. At time 2, is it speeding up or slowing down? Now it's starting to take off, and then at time 4, you can see it's really cool. In terms of our speed at time 0, are we moving forwards? Are we like speeding up? Is our speed positive or negative? Positive. So we're moving in a positive direction at time 0. But we also know that we're decelerating. So we're trying to be pushed back the other way. So at time 1, you can see that our velocity has become negative because we've decelerated. We've started traveling opposite to our original direction. And then that continues at time 2. Then at time 4, we've actually sped up a ton in the positive direction. I don't know. Acceleration. Sorry, that was supposed to be 10? Oh, 4, sorry. I probably just forgot to finish writing it. Okay, let's match up our graphs, guys. So, just to clarify, my displacement, I'm starting at 5, I'm back at 5 after a second, then I dip down, then I go up. Which, you reckon this is this graph? Does that match those points that we found? 5, 5, 3, and then, 17's off the page. So this would be our displacement. Our velocity, can you see that we start out lower, lower, and then high again? Which graph would be velocity out of the 2 remaining?
Yeah.
The first one, because we start here, lower, lower, back up high again. So this would be my velocity. I think you might be right. Now, something I want to point out, guys, can I get you to just look at displacement and velocity for the second? Can you see that where does displacement have its first turning point in that function? A half, you mean x equals a half, so about there. Now, at that point, what is the rate of change? 0 at a turning point. If we look at our velocity function, if you look at a half, what's the height of it? If we look at our other turning point at 2 and a bit, we look at our velocity graph, see they match up? This is just showing us the rate of change. You can see that as our displacement sort of skyrockets over on the right-hand side here, we do have a increasing velocity as well. If we then look at I'll use a different color here. If we look at our velocity graph, it has a turning point at like 1-ish, 1 and a bit. If we then look at our acceleration graph, same deal. It has a 0 at that point. So this one is showing us our rate of change. You also see, for this half of my velocity graph, guys, is my slope positive or negative? Negative, it's going down. And can you see that everywhere before that point on the acceleration graph is negative? And then if we look on the right-hand side, positive, positive. Slope is positive, the acceleration graph is positive. There's a direct link between what's happening in the velocity graph to what's happening in the acceleration graph. There is a direct link between what's happening in the displacement graph to what is happening in the velocity graph. Questions? I'm glad. We'll see how I go. We've got about 15 minutes, guys. Can I get to have a go at those textbook problems?